the same path can be set up and hold critical. Okay. And what do you think could be possible reasons?
Maybe different combination paths.
Same combination path. I'm talking
Different
about some.
combination paths.
No, no, I'm only talking that the same combination path can be set up and hold critical. Can you, do you know the reason why? Okay.
Endpoint will be the same for setup and hold.
Huh?
Endpoint will be the same for both
Yes,
setup and
start
hold.
point, end point, and including the data path, exact same data path. Everything can
Yeah.
be. So it, if it is same for the setup and hold, is it possible? If the answer is yes, why and how? Right?
Yeah.
Um, okay. So why it happens is there are few possible reasons. One is in the setup hold corner and setup corner and hold corner, right? The delay of the cell can vary because setup is in slow, hold is in fast corner. So what is the typical PVT for hold? For hold, the PVT is low voltage. Okay. You know, low voltage, low temperature, and fast process. What is the possible setup corners? Low or high voltage, sorry. For the setup corner, it is low or high temperature, low voltage, and slow process. For the hold corner, it will be low temperature, high voltage, and fast process. Typically, this will be your worst corners. Okay. And so what happens is across these corners, the variation of the cell delay could be, as I said, more than 3x or 5x or 6x, and that's because the delay of the cell is more. Okay, then you have to choose the right kind of cell. But mostly the reason why this is happening is, okay, the way the derating is applied, okay, on your launch and setup, okay, that could be a key problem. For example, um, this this is your launch path on your clock, okay, and this is your capture, and then we have uh, so what can happen is the derating, the way it is applied on the launch and capture, there is so much of crosstalk. Okay. And for setup, if there is too much of crosstalk, okay, especially on the clock, okay, it will impact it inversely. Okay. So the crosstalk, wherever it is there on the clock, it will, the way it will simulate is the crosstalk when it is doing setup, it will make sure the launch is actually arriving very late, and it will make sure the capture is arriving early. Okay, if there are crosstalk on the launch and capture path, but it will reverse that when it is doing the hold. It will make the launch arrive early and capture arrive too late. Okay, so that means your clock skew, the way it is seen in your setup, will be completely different the way you are actually looking at the hold. Okay, so the crosstalk is a key major problem for your setup hold analysis when you are doing for the exact same data path. Okay, so you have to kill the crosstalk in that context. So whenever you are doing this analysis, you have to enable the incremental delta delay also, so that you can find out what is the contribution of your crosstalk. The second aspect is for the, while it is doing the setup analysis, it will trace the clock path for the launch through the, fastest possible path to the launch, right? So let us say the clock can arrive in 5 different ways to the launch. It will trace the fastest path where the clock is arriving to the launch, okay, for the setup. And similarly, it will capture the, you know, sorry, it will capture the slowest path for the launch, and it will capture the fastest path for the capture, so that your clock cycle is totally shrunk. Okay, and that's the way setup analysis is done if there are multiple uh, clock paths for the same clock pin. Okay, but for the hold, similarly, it will assume that the fastest path for the launch and very slow path for the capture. So it will reverse that scenario. So because of the clock paths being different, the data path, even though the data path is the same, you will again see that the skew variation between the setup analysis and hold is different because the clock path is different, and that's the reason you are having setup hold critical data path. Okay, in which case you have to fix the data path. Okay, you have to go fix the clock path. You have to go and add buffers in the clock and make sure the clock convergence paths are similar, similar to the ones that you are seeing in the setup. Okay, or you have to balance the delays of your clock latencies in that case. So that is the other possible reason why you will have setup hold critical path. Are you understanding?
Yes, sir.
Yes.
Okay. So so the clock path, that is another variation. Crosstalk is another variation. Third one is, as I said, right, the delay of the cell across the corners, fast and slow corners, being different. Okay, so all these are possible reasons why your same data path could be, you know, critical path both for setup and hold. In which case, I have already spoken about the solution. Okay, so you have to implement the proper varying cells. You have to implement, you have to kill the crosstalk, or you have to work on the, whichever slow path or fast path launch is there. There also you have to actually act on the balancing of that. Okay, that's the way you will resolve the problem. The other issue with CTS would be that, if CTS is causing congestion, right, and you're seeing that, a lot more route has got added. Okay, first of all, for CTS, you have to specify middle layers for your clock routing. Okay, so that means, if you have like M1 to M12, if you're building clock mesh, you will build it at the top layer. Okay, like M12, M11, that's the layer you will build the clock mesh, because so that you will not, sorry. Okay, the clock mesh will be built at the top layer. Okay, but whereas your all the interconnect clocks, you will try and build it, between M5, M4, M6. Okay, these are the layers, because lower level layers you don't want to build the clock, because that is required for the data routings, short routings, because your clock routings are all longer routes. Okay, so you want to use the middle layers so that you will get a better delay and it will not impact your congestion. So that's the reason you have to specify which layers for using the clock as well. Okay, so you have to give these constraints before even running your placement. Okay, because all this will continue with the similar pattern. Okay, and what are the other possible question? So what are the reports that you will look at in the CTS? You look at the skew report, you look at the latency report, you will look at the the logic levels, clock levels report, and then you will look at whether the NDR report you will look at, so that there are no failures. You can run scripts wherever the NDRs have not got applied. You have to make sure. Then you have to also check if all the clocks were implemented. Okay, you don't assume that I run the CTS step and all clocks got implemented. You should debug because some clocks may not have got implemented because that clock definition point would have blocked. So because of some exception problem or something. So that is where you have to go back and check your clock tree and make sure that all the clocks are properly implemented. Okay. So this is a very important. If you are seeing any high fan out after CTS which has not got implemented, you have to fix that. See, in the traditional methodology, earlier cases, we used to build the reset tree and the scan enable also with a high fan out net synthesis similar to clock tree. Okay, but now you can always do reset and scan enable as a high fan out net synthesis. You don't have to build it like a clock tree scenario. Okay, so you have to ensure that every clock is connected, and you have to actually, the way you will check is you will run all the multi-mode multi-corner analysis both in the test after you have built your clock tree, because initially you have built your clock tree in the func mode, then you have enabled your test mode to do incremental clock synthesis. So now you will do timing checks both in the functional and the test domain, both using the fast and the slow clock, slow corner analysis. So you will do all your setup, hold all the analysis in the propagated manner. Okay. Then the last part is you will also route your clock properly. That means you will do a detailed route for a clock before you proceed to anything else. So, and you have to keep the clock cells, more or less, majorly the hand placed cells like clock muxes, everything as a fixed attribute. Okay. Um, so that's about CTS. Any other question you have on this? Because I can move to the touch base slowly on the routing very briefly and quickly close the STA flow and physical verification. Okay, just briefly I will touch those things. Okay, because that's not my focus of this topic. Any other question?
Sir, at CTS stage, which VT flavor usually we prefer?
Okay,
So
so
for
at
the clock.
CTS stage for building the clock tree, as I said, let's say you have used 3 VT flavors in your design, which is your SVT, LVT, and HVT. If these are your 3 VT flavors, in case you have used the 4th VT flavor, which is ULVT, whatever is the fastest VT flavor, that's what you should use for your clock tree, because I said your clock should be your aggressor. Okay, you should try and use that VT flavor to actually build your CTS.
Okay, the fastest one.
Fastest one, which will be your ULVT or LVT. Okay, so like that.
Okay.
Any other question?
No, sir.
Okay, so let's go to the STA topic, right? So, first of all, after you have done your, before we get to STA routing topic, right? So, what is that is very special about routing is a very, very critical step. Okay. And there are, even though 80% of that is automated, okay, there are some key points where you have to actually monitor and make sure your route is happening properly. Before you do your routing, okay, you have to enable that, all your clock balance to your, IO timing is considering your average clock latency, okay, for your IO timing. Okay, average clock latency means all the latencies will be combined. See, there are techniques like this where they use max clock latency for your IO timing or average clock latency for your IO timing. Average clock latency is a good thing because then the number of clock buffers and adjustment to the IOs is minimal. So that is one. Second part I wanted to actually say, so that you have to enable before you do, because until this point, there's no crosstalk coming into your picture. Okay, up to CTS. Now in the route is where your crosstalk is going to really get applied. Okay, so before you proceed from CTS to route, the first thing you do is you will remove the skew component from your clock uncertainty, right? So let us say the skew was 50 picosecond, you have set and you have set a routing margin of some 50 picosecond. So you have set an uncertainty of 100 PS means you can remove the skew component of 50 PS and allow the routing to go with only 50 PS of uncertainty. Before you get into the routing, you have to make sure your data is timing clean. Okay, because your timing is only going to degrade after routing. Okay, unlike the placement where you can still manage with violations, you should not have many setup violation in routing before you enter routing, but hold violations are fine to proceed. Okay, you can actually think of, if you have actually added derating for your, ensure all the deratings are properly applied. Okay, and if you have actually added some route derate, right? So you would add derate for the net, derate for your RC computation, and actually because to correlation, because this is correlation with the post STA, etc. And then you would have actually added derating for the cell. Okay, if you have added any buffers like in addition to whatever is required, you make sure that that's all removed before you get into routing. Okay, you keep very, very minimal pessimism on the routing, but you have to at least have some good margin before you get to your route stage, because after route is where you will see crosstalk. You can remove that pessimism and then start doing your STA analysis. Okay, in route, there are actually many there are 3 and plus 4 steps in routing. The first step is, okay, global route you have done. Then it happens that, what happens is now it will do a comprehensive global route, and then it will go to your DRC based analysis, and then it will start assigning the track. So when it is doing track assignment, because global route is every for 7 tracks, it will assign one global route. Now it has to go exactly which global route to assign to which track, which of those 7 tracks. So because track assignment is a critical part, and it will go and do that with both setup and crosstalk aware analysis. So you have to enable, when you are doing routing, you have to enable crosstalk aware routing. Okay, that is important. Because if you disable the crosstalk aware routing, then you will have more problems. Okay, but you can play with this option. If you are seeing too many DRCs popping up, okay, with the crosstalk aware, then you can disable and see if the DRCs are going down, and then deal the crosstalk differently. Okay, so the crosstalk aware routing should be your default enabled stuff for doing your track assignment, everything. Then after that, it will go into the detailed route. Then it will go into aggressive DRC fixing, where it is going to actually attack your DRCs, block by block level, and it will do rip up and reroute. Okay. And those are all crucial steps, you know, in this. So routing, you have to understand that after every particular step, let us say after track routing, okay, the number of anticipated DRC should be very minimal. Before it gets to aggressive fixed DRC, you should always see your DRC count should come down. If you are seeing that your DRC count, after step 1, step 2, step 3 in your detailed routing is continuously going up, that means there is some problem. Okay, after you can see 10 steps, if still DRC counts are going up, then there should be some real hard problems. Okay, and some of the hard problems are that there could be some specific metal layer congestion or some specific area. In that case, what you can do is, in that metal you can apply route guides. Okay, just before you run routing, you can apply route guides for metal 3. If too much routing is happening, because of which DRC is getting caused, you can apply route guides so that routes get redistributed to some other layer. Okay, so route guides specifically are used in the especially in the routing step. And the other key part is, when you are doing aggressive fixed DRC, initially you should try and use minimal number of steps, maybe 3 steps or something, by which you should see convergence. If that is not happening for initially, it means there is some real problem. For the final iterations, it is okay. But when you are doing initial floor plan trials where you are trying to get a routing convergence, you should actually see that in couple of iterations, your route should actually happen fast closure. The next thing is, before you enable routing, you have to ensure multi-threading is enabled for your machines. Okay, because route step will use, the more CPUs you enable, the faster you will get your database, because route can attack separate independently, unlike a lot of other steps. Okay, so the more CPUs are present while running the route, the faster is your runtime. This is very important, how you use your resources for your routing. Enable multi-threading, which may use additional licenses, and if it's more than CPU, at least 2 licenses are required for running your route step efficiently if it is congested database. Do you understand? Okay, so and so look at all the RIPA pre-route, enable actually multiple, at least add like 8 to 16 CPUs at a bare minimum. And you can add even 32 cores or 64 cores, and give a good estimate of your RAM required, maybe 60 GB or 120 GB, whatever is the consumption of your data, it will tell you. Okay, and similarly keep watching on the route net length. Okay, it should not keep increasing. If you have resolved all your scenic routes earlier, it should be in a good shape. Otherwise, scenic routes are going to cause disaster during routing. Okay, because add buffer on route is going to happen, and then your timing will go for a toss. Okay, if you are seeing too many add buffer on route names coming up, that means on a detour net. So then a lot of detour is happening because of crosstalk issue. So go and investigate that. Okay, and uh, route steps are many. Okay, simple basic route, and then there is opt route. Opt route again is a step where you are actually going to do an actually optimization, setup optimization, and after that again you will do actual detailed route. Okay, you will do again second iteration of routing after op route to ensure that again you are reconverging, because you would have done setup optimization, hold optimization. After the basic routing, you're running optimization post route opt, and after that again you are going to do one more round of routing to ensure that the DRCs are covered. Then the final step of multi-VT enabled. Okay, that means here is where, because now when you are enabling VT swap, okay, that is power recovery you are doing, it will be looking at both the transition. If it's swapped to HVT, then suddenly it will see it's getting a weaker transition. So it will do that more detailed analysis when it is doing. Okay, but when you are enabling this VT swap, okay, you have to keep a track of how many DRCs and what is the timing impact before and after that. so that you after VT swap, if you are seeing too many timing degradation, you can swap back some of the VT cells. Okay, don't try and run another round of optimization. You just swap back some of the VT cells so that you will recover the timing. You should only enable VT reswap to regain your timing after, if you are seeing the timing degradation just of VT swapping. And all these steps are not mandatory. What I mean to say is it is not a must to run every single step. This is a choice. I mean, ideally, from a flow point of view, route steps, you can run these 4, 5 route steps. But if you are seeing that converging, after this it is degrading, you can probably stop up after opt route, or you want to actually manual fix your timing and VT, later, then you just can actually exit at the route stage and deal with it. Basically, depending on your project priorities, you have to take right actions. Okay. But any missing of these steps would mean, that certain optimization has not happened. So the ECO cycle will be tough. So you have to, it's a trade-off about how you are going to converge your timing. You understand? So route is not a dumb step. Route has a lot of intelligence. If I spend route, I can spend one full day talking about each of those things, going into detail, how you are going to do aggressive fix, what is that you have to do, what options are there inside route. So there are a lot of tool options. Okay. Uh, but here you are not going to do anything with detailing with the floor plan, but any mistakes you have done in the floor plan are going to be showing up in at least 100x during your route. Okay, you can be rest assured about that. If certain DRCs are not taken, certain floor plan DRCs are not fixed, they will become very costly affair during route. Okay. So before going to the route, your congestion and timing should be clean. It should be in good shape. That's when you should venture into doing route. Otherwise, you can do just 2 iterations of route enable for a simple tracking of how many DRCs could pop up just to estimate, because without cleaning that, going for a full route is going to be very expensive affairs. It may never end also. It may keep running. So managing your resources, giving proper CPUs licenses is very important. At the same time, checking these things, prerequisites are also very important. And while doing route, you have to ensure that, first initial route, there is no fill applied. Okay. Then basically opt route when you are running optimization with setup. Okay. Again, no fill required. But after that, you have to actually add a fill. Okay. Add fill step is an important step. After adding fill, again, you will have to route. Okay. Now, first is you will add a base fill, you will route, then you will add metal fill. Okay. When you are adding metal fill, more DRCs pop-up will happen. Okay. So it will have to rip up some of the fills, tool will take care. So add fill, route. Okay. Then change names, route. So many intermediate steps will happen. Watch out. Okay. Where the filler addition is causing problem, issues could be anywhere. So you'll have to debug that thoroughly. Routing is a very important step.
Hello. Sorry to interrupt,
Yes.
sir. You are having network issue. If possible, tomorrow you will join for the discussion.
Okay, that's about route. Any questions? Any questions on routing? Have you faced any interview questions which you want me to answer? Okay. Let's move then. Yes, go ahead, Pooja.
Sir, in the interview, they're asking after routing what we need to check. What is the important thing we need to check after routing?
Very good. Okay. So what are the key things that you are going to check post route? Okay. Post route, you have to actually run verify LVS. Okay. Verify DRC. Right. your DRC and ICC DRC and ICC LVS should be clean. Okay. If you have minimum number of DRCs, because even whatever you may say 100 DRCs, actually in the PV it may show zillions. Okay, you have to be very clear. There should not be any power short. Okay, at the route stage. All right. And you have to actually also see how much is the route length change between your global route, post CTS, and actually your net length post route. If you are seeing more than 3%, 2%, 3% variation, then there is some problem. Okay, there is a lot of detouring which has happened, which would cause you a problem. Okay, and in the log file, if you are seeing that the DRC iterations have caused, or so route length is one thing you will check. Then you will check DRC, you will check timing, you will check actually, filler addition, whether the metal fill is completely done. Okay, base fill is done, legalization check. Okay, and you should also check post that if you have actually multi-power domain, right? You have to ensure that the routing has happened, taken care of that properly. Okay. And the other thing is, the crosstalk effect, because this is when post route is when you will see how your crosstalk timing, because suddenly your timing will look bad during post route optimization. Okay, crosstalk enabled, etc. So then what you have to do is how the crosstalk is getting eliminated. What are the things? How many crosstalk nets? How many delta delays are there that needs to be fixed? So things like that you'll have to check post route. Okay. So your timing, your DRCs, because there's no idea, you can still look at a congestion report, which will give you some perspective, but it's more now to look at for DRCs, routing, legality, crosstalk, and make sure the chain names and GDS dump is happening properly. Okay. After route, you will have to dump actually one netlist, which is purely for LVS, one netlist for doing formal verification, okay, which is different, and netlist for formal verification and netlist for, this one, what is that? Timing analysis could be same, but for LVS, the netlist will be different because you'll have to enable all the power nets, everything to be visible. Okay. And for LVS, so LVS netlist you'll have to dump. So you'll write the OASIS file and make sure those are all coming out clean. If you have any issues with the chain names, okay, it will pop up the errors. So you'll have to clean that up. Okay. So routing is a very important step because this is where you are actually going to submit the data for the final analysis. Now is a step, because post route only you can run IR, you can run EM. Okay. Post route, you will have to give the database one for IR, EM analysis. So one question that could come is, what is your IR drop corner? What is your EM corner? What will be your IR drop corner or EM corner? What will be your PVT conditions for your EM? Can somebody answer? See, there is a PVT for library and there are some, extraction for your net. Okay. For the EM electron migration, the idea is it is capacitance dominated. All your electron migration is capacitance dominated. So the thing for that is you have to look at WC corner, worst case cap for your route. Okay. From a process point of view, the worst is going to be your fast corner. Okay. FF process. Voltage should be your highest. Okay, because that's when maximum current is going to go and your EM impact. So voltage will be highest. Okay. Temperature also will be worst, because when temperature is worst, Okay, that's when you will see that, lot of hot electron effect will happen and rip up will happen. Okay, so unlike your timing corner, for your worst case EM will be WC for your extraction, for your star XT, and then for your library it is going to be FF, best case, I mean maximum voltage, and you know temperature will be also maximum 125 degree, 140 degree. So that will be your temperature for your EM. For your IR drop, only WC will change to WRC because your resistance effect is the most important thing for your IR drop. Okay, so WRC, WR should be your corner for your resistance because that's when the voltage drop is going to be seen. Is it clear?
Yes, sir.
Okay. Now, when you are looking at STA, initially you have to run on critical corners only. Don't run too many corners. You may have 160, 200 corners. Not every corner need to be run. First, you have to close the critical corners, which means critical for setup, critical for hold. Okay. So the way you will do your timing analysis here is you will run for your setup WC, which is your net case. Net extraction will be worst case capacitance. Okay. And WRC. So two possible extraction corners. For the library, you have two possible, when you are doing setup combination, you have two possible, PVT corner, which is your slow, okay, low temperature, low voltage, slow, high temperature, low voltage. Two PVT corner for your standard cell, two corners for your extraction. So a combination of that is four corners. These are your four setup corners where you will do your analysis. Maybe you can narrow down to one or two depending on how your timing is looking. Okay, but run one or two corners for setup and one or two corner for hold initially. Converge that. Get close to like less than 100 PS before you are looking at the other corners. Do you understand? So post CT, post route, before you get there, you have to enable, you have to check your skew. You have to check because if skew is showing really big, that means there is crosstalk on your clock tree because of clock route coming in. So you have to eliminate all that crosstalk, on your CTS before you are doing your proper timing analysis. Okay. And now what you have to do is, so you will start with this. You may have 10,000 or let's say 1 lakh violations, 100,000 violation. Okay. Now, while you are running your STA, okay, run it initially for a n worst of 1. That means one worst path for one endpoint. Okay, one start point for one endpoint. If you are running n worst of 10 means 10 possible start points for one endpoint. So that's the meaning of it. So you run initially for n with n worst 1 and check which are the paths, and then first focus on, before you attack anything, the way you run your STA is check the DRVs. First clock DRV you have to fix. Okay, clock DRV also, net length, cloning. Okay, these are the things that you have to look at. If your net length is because there's a big fan out that has happened. Okay, first you clone and tie that up. Make sure the clock tran is in good shape before you address anything. That is the one. Parallelly, any net length which is more than, let's say 300 micron or 500 micron or 700 micron, whatever you criteria you come up across. Okay, ideally anything more than 300 micron, you just go and add buffer on route. Okay, so this should be get nets for all that, whichever is violating more than, all the violating paths, whatever you have, you dump out all the net lengths. Any net length which is more than actually 300 micron, you can go and buffer them. Ideally, 500 micron should be your initial start point. So just buffer those nets so that add buffer and middle. You should add buffer at the middle. Okay. And for a clock tree, you should do a net splitting. Okay. Enable the net split so that the cloning happens, then the clock tree will get split according to that. Okay, so you have to do this properly. Then, so address the clock transition first, and address the data lengths, whichever is the long nets. So these things you can attack parallelly before you start looking at any setup fixes, etc. Okay, so fix this particular DRVs. If you're seeing that these are in good shape, okay, then you can address the cap violation, similarly long nets, okay, things like that, and then start working on your actual timing violation. Is it clear? And this you can easily script. Okay, get net length more than 700 get nets. Okay, get attribute get length, net length greater than 700. Dump out the net for each net. Okay, add buffer on route. Okay, that's the stuff. And then you can add it. You can give the buffer name, add it at the middle. Use a buffer which is middling buffer like 4x drive strength. Don't use very high drive buffers. You understand? Or very low drive. 4x, 5x is a good drive strength buffer. Use that. Is it clear? So then, okay, you'll have to segment. Before you attack the setup time, you look at the histogram of the setup time. Okay. Let us say the violation are basically between WNS. For the setup, you have to address the WNS. For the hold, you have to address the TNS as a maximum. So WNS, when you are looking at it, because and what you can do is, okay, let us say you have like 10,000 2 nanosecond or 3 nanosecond violation all the way up to 0. First you fix, you'll have to structure. I'm going to address between 500 picosecond to 3 nanosecond to the worst nanosecond. I'm going to address. List out all those paths. See what are the bottleneck cells which are actually low drive, just upsize them. Okay, or look at already you have addressed the DRV, so go and fix that. Okay, and you can actually look at it if that is because of a clock skew problem. Okay, address it, address the clock skew, address those particular issues before you move to anything else. And then you can work on your clock drivers. You can work on your weak driver cells in your data path. You can upsize them. Then you can address all the net lengths. And that's the sequence to address that, all the bottleneck cells, so that all violations will be attacked simultaneously. If you don't follow a proper structured approach, you will start working on one-to-one path. No, that's not the way. So grep, you have to, this is where you have to use a lot of your unique skills. Okay. Dump out all violations between 500 to 1000 into a single report. Okay. Get all the cells, okay, with violation. Okay. So you can write a script saying, cell delay, column 4, delay greater than 40. Okay. Get cell name, get column 2, dump that. Okay, I can show you, you can write a script and then you have to uniquify those cells so that you will get, some 100 or 300, whatever is the list. Only those cells you have to do, not upsize it each time. Hello? Now meeting later. Okay. Okay. So, so addressing them systematically so that you are able to bring down less than 500, next address between 100 to 500 or 300 to 500 before you start looking at the lower end of the violation. So this is how you have to move in terms of addressing your set of fixes. Similarly, once you are actually reasonably confident on your setup, because all skews you will try and do with your setup, if you have to do like, especially over here, fixing clock gating violations are huge challenge, because you do a clock push on your clock gating. Because clock gating, you should understand, at placement level, you won't get so many violations. Okay, one of the key things after CTS, what you will start seeing, new unique violation is clock gating violation coming up. Why? Because what happens is your clock gate is part of your clock tree. Okay, and that will always be always have more skew. Because your clock gating, I told you initially itself, you have to keep clock gate cells as close to the sync points as possible so that the skews are done. But there will be architectural clock cells which when you sit in the middle. So for that, because the clock skew will be more, for clock gating cells, you can address it them specially in placement also by giving extra margin. Okay, set clock uncertainty for those particular clock cells, maybe 500 or 300, because if you are estimating that kind of a skew, okay, so that the data paths could get optimized. If you have not done that, then first thing is you have to figure out, whether I have to do early clock for fixing that clock getting paths, because they are very, very critical and it has to be fixed. Okay. So fixing clock getting violations are going to be something which is going to appear new after post CTS only, which you will not see in the placement. Be very clear. They are all new violations which are going to come. So you address more and more violations upfront in placement and various other stuff, so that your focus, your problem areas will be more minimal. Otherwise, your problem areas are only going to keep expanding, because new issues, new complexities, like in post CTS to later stage, you are going to see clock gating. Post route, you are going to see crosstalk enablement. So all these are going to add factors to your timing challenges. Is it clear? Okay. There are so many things to talk in the STA. Okay. Now let's talk about hold fix. Hold fix, as I said, right? Don't look at all endpoint and just add buffer. That's not the way you run STA. Hold fix for the STA should be like, first you adjust the clock skew, minimize it. You, as I told you, swap the, let's assume that you have done all your MVT. Now you have to only look at, clock fixing, buffer fixing. You do a start point fix as your first step. Okay, that means you try to add buffers with common start points. Okay, there are like it could be like 500 endpoints having a single start point. So you add one buffer at the start point, all the endpoints will get fixed. Okay, so first you have to proceed with start point fix for your hold fix. Then you address the bottleneck fix before you look at the endpoint fix. Okay. And setup also, initially you might have run with n worst of 1. Then after you have got a little convergence, you are seeing like, okay, if you think I have addressed with n worst 1 between 3 nanosecond to 500 picosecond, I have addressed. You have addressed that problem. You are seeing that that path has got fixed. But once you are doing update timing, suddenly you are seeing still your violation is 2 nanosecond. Same endpoint is coming, but now it will be a different start point or some other combination. That's because your inverse is taking factor. So you'll have to sequentially start increasing your inverse to 10. Then when you are getting closer to less than 20, 30 picosecond, run inverse 10,000 or 1 lakh, like that, so that all the violations are seen and addressed. Don't assume that inverse to address, no. Because the moment you keep it, you'll keep getting the same paths pop up every time and you'll get frustrated. So, but at the same time, if you enable 1 lakh inverse at the time, you will see so many paths. How will you address them? Your huge report, to process that report itself will be very difficult. Okay. So this is where script comes in. You have to use the technique of using the NVERST smartly. Okay. So as I said, timing closure. First thing, DRVs. Next, you will work on actually, any illegal clock cells, etc., that you have, you clean up at this point. You have to look all the things, metrics in a comprehensive manner. You will have actually double switching violations. You will have min pulse width, address the min pulse width and min period violations. After your initial placement and initial estimation, if you have got min period violation, that means there's a problem with which, it has been specified at an earlier stage. So that should be reported to your RTL or your library team and fixed. If you have min pulse width violation, look at the library cell, which is causing this problem, or your transition issues could have caused this problem. So you go and fix them. Okay. Then double switching, long nets. Okay, all these are standard violation which you'll have to just buffer and take care of crosstalk properly. Just buffer them, buffer the nets. This should be good enough for you. Okay. Yeah, any big driver cells, all that you swap back, you should not use anything more than 8x, 10x drivers, because that will cause you EM violation. Okay, and it would cause you different. Only when you are using top level for the long nets, you are driving 200 big fan out. That's when clock drivers can be 24x or 12x or 16x. So they are supposed to be used by expert analysis only. You have to use it very, very carefully. Okay, high drive and make sure those are all taken care. Then you will get feedback from your IR drop. I have this, you use your decap. As I said already, you should have used fillers. You should specify before you run filler, what type of fills you should actually use before you run routing. I have told you, right? Should enable the fill such that at least for every one of the 4 filler cells is a decap. You can enable like that ratio. You can enable ECO cells in your fillers. You add that adequately. 50% ECO cell you can enable like that. So that's where it will spread out properly. Okay. So that's about STA. Now, any questions on that? I know I've rushed that through. I'm not given it detailed, but understand STA, the steps are like this. You're going to dump out the netlist and the def. Okay. Route database from this. Then route database, you are going to run extraction. So the extraction will dump out different WC, WRC, etc. I have told you. Take that. Similarly, from the netlist, you will have to take whatever the library required and then use that. Worst case, PVTs, etc. I've already explained. Then you will run PT session separately. Okay, setup session with WC, WR, whatever is the combination of your route and this one. For each one, you'll have to run one PT session. Okay. And for the in the same PT session, you can dump both setup and hold analysis report. But when you're doing setup report, it was, as I told you, it is going to trace the worst case data path, the worst case launch path, but best case capture. This is the what it will try to track when it is doing setup analysis. Okay. So be aware of that, how the algorithm is going to look at that and analyze and address them appropriately. Now, let's go to that physical verification. Okay, physical verification PV steps are like this. First is you have a GDS which is dumped out, and then you have a LVS netlist. So with the netlist, you have to do V2 LVS. So you have to convert that netlist to the SPICE netlist. What is that step meaning? You only have this particular net connection over here in the netlist, pin A connected to pin D. That's what we'll have in your ICC. Okay. But what is the device? The device information will happen in the V2 when you're adding the spice for that. So, and to this one, all that spice information will get added for your netlist. Okay. And then similarly in the GDS, okay, what you have dumped out is only metal GDS. Then all the base layer GDS will get, you have to do a merge GDS. You have to add all the library GDS, then perform the merge GDS option, because that's when you will have a total GDS. And from that GDS, you have to do an extraction of your netlist for doing your analysis of your LBS. So, and then with that merge GDS extracted netlist. So for this, again, you will have to give all the rules. Spice rules, rule deck is another input. Rule deck, V2 LVS for converting into Spice netlist, because you cannot directly compare your ICC netlist with your GDS netlist. That's not the way it works, because device netlist is what you want. Okay. So device netlist, and then extracted from your merge GDS, again, another netlist will come. So that is when you will do the extraction. One thing while doing the, star XT extraction, the star XT also can dump out certain shots. It will tell you these are shots. Okay, you have to fix those shots in your design. Okay, not shots can be shown in your LVS shots. Some of the shots can be shown specific to your extraction also. So all shots are important. Everything you have to fix. Okay. And so once you have this particular analysis, okay, then similarly for DRC, you have GDS extracted, and then from the DRC rule deck will read, and then it is going to analyze this net. Okay, is violating this rule, etc., etc., and then that's it. You'll lose a layer map file. Okay, for all the GDS views. Okay, you will add that layer map file, merge GDS spice information, then all the library GDSs should be read. Okay, etc. for this. Okay. Similarly, for a Raya drop analysis, okay, for the memories, you will have to use the transistor model. Okay. Fully extracted transistor level model is what you need for all your hard macros, be it analog or your memories. For your standard cells, you don't need to go up to transistor model. Gate level model is good enough. You can enable port model, okay, for your IR drop and EM analysis for your stuff. So that's what you need. That's where you have the CDL models, okay, available for your electrical analysis, okay, like IR, EM, and any crosstalk noise analysis. So this is what you're going to use. That's just the flow. I cannot teach you, different rules on your PV right now on this online. Any questions? So they may ask you, tell me how you are going to do. What is, some of the questions is, because this is more to do with PNR. I just gave you an extension. So focus on your PNR aspects only, because this is a PD interview. Okay. Any questions on the PV? What? Because so many things are there. I can explain, I will take that video also to tell you different stuff, and ST also. Just I gave you an overview right now. Okay, guys, it's 9:30. You can go to your dinner. You can break off if you don't have any questions. Okay, anything else? Shall we conclude? Okay. Yeah, Sridhar. Pooja, you have some question? Okay. All right, bye. Take care. Thank you.
Okay, fine. Thank you.
Thank you, sir.
Bye, sir. Thank you.